All right, last day, we got to the point where we were talking about triple covalent bonds, and if I had like 5 more minutes, I would have been able to give you some homework, but I didn't. So we've got to finish off talking about triple covalent bonds, and then I've put a bunch of examples of possible Lewis structures that you can draw. So we'll work on those together. And then also today I have to talk about one more type of bonding, and no, unfortunately it's not quadruple bonds because they don't exist, but it is something called coordinate covalent bonding, all right? And so that's the way it's going to look for today. We'll be practicing some diagrams, and I actually have the first of a couple of assignments that we'll be doing next week, and you guys will be able to do the first half of this page from the information that I've given you. What I tell you on Monday, you'll be able to do the second half. So I didn't get to the point where I gave this to the first period class, so you'll be able to get a little bit ahead on that, get that first half of the page done. It really is not that difficult. Again, just to kind of refresh our memories, the triple bond, what am I putting in here for our blanks, is formed when 2 atoms share 6 electrons. 6 electrons, yeah, this is not big information. We'll get hands up a little bit later. Each atom contributes 3, all right. And I, again, in a hurry, didn't want to necessarily draw the electron dot diagram, but again, just to refresh our memories, and if you'd like, you can put this down. It might help you clarify things, but it's not a big deal. In terms of N2, all right, remember each nitrogen has 5 electrons, and I've oriented them in this fashion so that I can put the other electrons, or the other nitrogen's 5 electrons in that orientation. And I'm hoping from yesterday's work, it doesn't take much to imagine that we're going to have 3 sets of overlap here, which then ultimately results in a triple covalent bond, and then our lone electrons, all right? So again, when you're telling me how to draw things, that would be, you know, pronounced as a triple bond, all right? Again, just to make the note kind of fit with what we've done in the past, this is a triple bond, and there are 6 electrons in that thing, all right? And again, when you're drawing your structures, the rules that we need to check, what did we call that rule to make sure that everything was happy? What did we call that rule where everything was happy? Yeah, go ahead. Yeah, the octet rule. All atoms will share electrons in order to get 8 electrons in its outer shell. So we consider this bond to belong to this nitrogen, 2, 4, 6, and 8. And we also consider the same for the other nitrogen, 2, 4, 6, and 8. All right? And therefore, those nitrogens are happy. We've got a nitrogen that looks the way we think it should look, and therefore we have a good structure, a good Lewis structure. All right? Just to kind of, again, review from yesterday, if I were drawing something in group 17, I'll start to the right because group 17 is on the right. If I were to draw something like an iodine, what should it look like when it's bonded in a Lewis diagram? How many lone pairs and how many bonds should it have surrounding it? Yeah, Lily? 1 single bond, and what else do I need to complete that picture? Yep. 3 lone pairs. 1, 2, 3, 4, 5, 6. All right? And that, remember, comes from the fact that it comes from group 17, which means it has 7 valence electrons, and that one that's on its own will form a single bond. If it's in group 16, like, let's say, oxygen, what's it going to look like in terms of bonds and lone pairs? What's it going to look like? All right, Cole? It could have a double covalent bond, but it might just have 2 singles. 2 singles or a double, as long as it's got 2 lines coming from it, and 2 lone pairs. All right? And yes, when we get doing the summary examples, they're going to have singles, doubles, triples, all kinds of different things. Excellent. And if we're talking about something in group 5, and this time we'll just pick phosphorus, what's it going to look like when it is in a Lewis diagram in terms of bonds and lone pairs? Yep, Justine? Yep. 3 bonds in a lone pair, and whether it's 3 singles or a single and a double or a triple, it doesn't matter as long as it has that structure. Excellent. Again, that's because it's in group 5, 1, 2, and then the lone ones have to pair up, 3, 4, 5. And then we're over to carbon, and really it is only carbon. Silicon very rarely does, but we might have a silicon example. And what's carbon going to look like when it is bonded? Yep, Cindy? 4 single bonds, or 2 double bonds, or a triple and a single, or any of those types of combinations. All right? Okay, let's do some examples now that just contain triple. So we'll put these 2 up. And these are examples of triple. These are triple examples. And then in the next slide, we'll do a summary, a whole bunch of them. We'll draw them all up. They might have all singles, maybe double and a triple, all kinds of different ways. These examples here contain an example of triple. There's probably other singles in there as well. Again, I'm looking out there. Some people are diving in. We're drawing bonds. We're drawing all kinds of stuff. Don't forget, if you're not sure, right, draw all your atoms out with all of their possible connections. And then here's where imagination comes in. You've got to kind of visualize where those connections are going to go. And then we need that final molecule. Does somebody have a possible structure for HCN? Yep, Bradley, what do you got? Sorry, I want to do the top one. That's okay. Have you got the top one done? Okay. Yep. All right. I'm going to put the carbon on the left just because it is on the left in the name. Yeah. And what else? Yeah. Excellent. One more thing. One lone pair on the nitrogen. Excellent. Checking the octet rule. 2, 4, 6, 8 on the nitrogen. It's happy. 2, 4, 6, 8 on the carbon. It's happy. Hydrogen only needs 2. It's good. All right? If you were drawing this using this tactic here, you might make a connection there. You might make a connection there and a connection there with a connection there. And that's the same structure. It's just not as neat as the other one. Okay? On to the next one. Somebody have a suggestion for that? Zach, you got something there? Nope. Okay. Marcy, what do you got? Okay. Off each of the carbons. Excellent. 2, 4, 6, 8. 2, 4, 6, 8. Everything's happy. All right? Okay, so now just kind of as a summary to check for some understanding, let's just bring up a big long list, and you can start drawing them, all right? Now, ideally, I would get the whiteboards. Remember the whiteboards we used? Now, Mrs. Murray's using them right now. When she's done with them, she's going to bring them over. So start working on these, but in a moment I'll distribute some whiteboards, and then you and a neighbor can maybe check each other's work, or maybe have some ideas on how to draw that if you're still unclear how to do that. You don't have to copy them all down. Write one down, draw a structure. All right? Now this last structure right here, and you'll notice the second last one, we guide you a little bit on how we want the connections made. All right? You'll notice here I've got a C with 2 H's, and I'm doing that on purpose, and then a C with an H, and then a C with 3 H's. Same with this last one. This last one, you might notice it from the back of your periodic table. Without the H, what is that SCH3 COO called? Yeah, Braden? That's acetate. When you add the H, it becomes what is called acetic acid. All right? Does anybody know what acetic acid is commonly known as? What is acetic acid? Yeah, Bradley, sorry? It's vinegar. So this molecule right here is the active ingredient in vinegar. And it's a tricky one to draw. See if you can do that one at the end. We'll see if we can get a good structure on it. Start the recorder again here so we can take them up. Okay, what do you got, Marika, for the first one? Bromine to phosphorus. Yep. Yeah, and then lone pairs on each. And again, lone pairs here. And how many on the phosphorus? 2 electrons, 1 lone pair, right? Okay? Are we okay with that one? I'm going to clear the screen each time on this so we can see it clearing. Next one. Who's got the next one there? Somebody want to tell me what we're drawing? Yeah, Carissa, what do you got there? She's sitting there smiling away. Oh, okay. Iodine. Yeah, iodine's fine. Yep. Yep. Yeah, iodine. How many lone pairs on the iodines? And when you say 2, you actually mean 1 lone pair, right? 2 dots, 2 electrons. That's a good picture right there. All right. We'll clear the screen again. SCH3OH. Somebody have something there? Christy does, I'm pretty sure. What do you got? Three hydrogens with single bonds, right? Two pairs. Excellent. Again, when you're given something like this where they don't pile up all the H's, we're giving you a hint on what's being connected to what, all right? And that's the way chemists do that, especially for big molecules. Okay, let's keep rolling. Next, we got one. This is an easy one. Should be diving in on this one. Bradley, what do you got? Yep, and it doesn't matter where they go. On the sulfur, I assume, right? Again, always check your octet, all right? Those people who are still stick handling things and putting it together, when you're done, make sure everything's happy. 2, 4, 6, 8. H's only need 2s. That's a good structure. Okay. Next. Who's got it? Yeah, go ahead. What do you got? Carbon. 2 hydrogens singly bonded, 2 bromines singly bonded. 1, 2, 3, 4, 5, 6. I'm going to cheat and jump ahead because that's what you're going to tell me to do, right? We're getting good at that. Excellent. Next, what do we have for that one? Yep. Mm-hmm. Mm-hmm. Excellent. Those are all following the rules that we need to follow. Excellent. Again, if you check the octet, it's good. Okay, next. What do we got? Yep, Marika. Yep. 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 3 lone pairs, yep. On phosphorus, I assume, right? That's a good picture. A question, Cole, or are you giving me the next one? Okay, giving me the next one. Clear? Go ahead, Cole. Okay. Yep. Okay. Yep. Excellent. All right, that's a good structure. Again, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Excellent. Now on to our acetic acid. All right, so what do we got here? Clear the ink. Acetic acid. Braden, what do you got? This is exciting because I haven't checked his final work here. What do you got, Braden? Okay, this is exciting. Yeah. Oh, yeah, it's a true statement. It's fun now. So you want a hydrogen off of this guy? Single bond from a carbon to another carbon. All right, this is fun. You're going to run into trouble right here because you have, right now you have too many double bonds. At this point, it's fallen to pieces. Actually, it fell to pieces a long time ago. I just thought I'd let you keep going. Sorry. What did you want me to do here? I think I'm doing nothing at this point. I think here's the move right here. Look at that. There we go. What do you got there, Jenna? Fabulous. That is acetic acid. That I would put on my French fries. But there are other versions of this, all right? We call, when we have more than one structure for the same formula, we call them isomers. You don't have to worry about that term in this course. But again, iso, we've seen iso. What does iso mean? No? Alike? No, same. It means same. In this case, it has the same formula. Marika came up with this. And then I think you had an O, and then an O, and then back to the C, right? A ring structure, which is, it's fine. And then what did we have? We had two H's off of each of these, right? Now you'll notice that it's got all the proper numbers of H's and the numbers of C's and the numbers of O's, but that is definitely not acetic acid. We could make it. It would have very different properties. I definitely wouldn't taste good. I'm guaranteeing that. But again, I would give you full marks for that. Somebody else also had another structure. I can't remember who suggested it, but I think it was a carbon with a double bond carbon. Then where did it go? Who had the double bond in their carbon structure? Did you? Yeah. What did you have at that structure? Oh yeah, that's right. Then we're singly bonded. Oh yeah. Singly bonded to O, singly bonded to another O with an H on the end, and then two H's, and then one more H, right? So there's our 3, 4, 5, and then the O's, all right? Again, not acetic acid, probably quite unstable because an oxygen bonded to an oxygen is usually unstable, all right? That will usually break apart and give off oxygen molecules. But still, that contains all the right rules. Everything is happy. Everything's connected. I give full marks for it, but it doesn't happen that to be vinegar, all right? Excellent. Let me talk about one more type of question that you can encounter. Now, for these guys, when we deal with, all right, when we deal with bigger molecules, another way we can help you is by giving you a skeleton structure. This structure contains all of the basic connections of the molecule, but it doesn't have the double bonds, the triple bonds, and the lone pairs. So what I want you to do with these is I want you to add appropriate double bonds or triple bonds or lone pairs so that all of the atoms are happy, all right? We're using the same rules as we did a moment ago, but this time I've given you the original setup. You just have to add bonds and lone pairs as our atoms dictate, and we'll get a complete structure. You can't add any extra H's or O's. We want you to just add some bonds or lone pairs so that everything has their proper order. So here we're dealing with carbons. How many bonds do all of the carbons need when you're done this process? Yep, Carissa? 4. So you need to add some bonds so that all the carbons have 4 lines coming from them. And all the hydrogens have 1 line coming from them. So now we need to think a little differently. We're adding lines so that all the things are happy. Same with down here. You're going to add some lines to make double or triple bonds. You're going to add some lone pairs if it needs it. What I would do, draw your structure like that, draw the skeleton in pen, and then answer it by adding your dots and your lines in pencil. And then if you screw it up, you can fix it. But you guys just work with pen anyway. Nobody listens to my pencil suggestions anyway. Crazy. What's the matter? No, we're not doing the whiteboards. Change my mind. Suck it up. The only reason you want whiteboards is to play. Yeah. No, it doesn't. Let's go through the first one just so that everybody knows what's happening. Does somebody have a suggestion on what I need to add so that all these atoms have their proper number of bonds and lone pairs? Yep. Yes, and you can only use them in this order. In actual fact, all I'm doing is I'm either adding lines or dots such that all of my atoms look like they should. In other words, carbon needs 4 lines. So the carbon could look like this, the carbon could look like this, the carbon could look like this. All right? If I've got an oxygen in it, it's got to either look like this or like this. All right? So all I'm doing is completing the picture with extra lines and dots where needed so everything looks like it should. You finished?
No, I'm waiting.
That's no fun. It's not tricky.
Oh, wow.
What's that? I'm adding lines or lone pairs. That's it. No, because does carbon normally have lone pairs? So I wouldn't add lone pairs to carbon. Did I screw that one up? I think I did. I think I'm missing one atom. In my haste, I'm missing an atom. So let's put this right there. Sorry. It was. It was impossible. Not only was it tricky, it was impossible. You connected the 2 carbons together. Yeah, that would, but you'd have to make it a triangular structure. It wouldn't be very stable. You could make an explosive out of that. Okay, now that I've taken the confusion away, what am I doing to fix this? You're right, I still can't do it. I am screwing this first one up big time. I need another one of these. Actually, why couldn't we do that? No, we still couldn't. Now it's easy. What am I doing? This is disappointing. Actually, I still think we should be able to do the first one. All right, I'm clearing that first one. Let's take a look here. Let's get rid of that. Clear ink. This is what I wanted, but what are we still missing on this? 4, 3. I needed this and this. This and this. Okay. That was an absolute failure. Let's take a look at the second one. Hold on, let me look at it first. Yeah, that one works. God, I hate it when the first one fails so epically. That's fun. I'm actually very pleased that you determined that my first one was a failure. Because it's better that it's better that you realize instead of trying to jam it in. But that did work. What you had there did function. Okay, what am I doing for this one? Suggestions. Where am I putting various bonds and things? Go ahead. This one here? Yeah, oh, I was going to change color. Very good. Yeah, and what else to finish it off? I need the lone pairs. One more situation. Oh, did you say the other oxygen as well? I missed that. Maybe you didn't say that. All right, let's try one more. Let's do one more. I don't know. Of course, you've got to question it. Who knows? Who knows? It's a mystery whether it works or not. I don't know who made it up. I don't know whose handwriting that is. Whoever it is, I'm going to find out, and I'm going to have to talk with him. Okay. Or her. Oh, no, it doesn't work! No! Are you kidding me? We run into trouble here! I gotta go boom. No, no, it's good. It's good. It is good. 3, yep. We can do it. Whew. Don't second guess yourself, Sanders. You know what you're doing. You've been doing this for a while. You can do it. You can do it. All right. You have it? Patience. It does work. All right, Mariko, what am I doing here? Hey, okay, keep the murmuring down. Go ahead. First oxygen, what am I doing? Lone pairs. Hey, listen up, folks. Go ahead. Double bond between the carbon and the nitrogen. I like that. That gives that guy 4. That guy's 4. The nitrogen is looking good. Lone pair on the nitrogen. Double bond on the oxygen. Okay. 2 lone pairs. Does that take care of everything? Makes everything happy. Everything looks the way it's supposed to. Excellent. Good. I do have a little bit of a sheet now. I'm going to hand that out at the end. That was just the end of our kind of a summary that deals with these things. There are a handful of questions out of the textbook that you can do, but I'm going to save. You can save that for homework, so you can write that down. And like I said, at this point, you can complete the top part of this little assignment. It's going to be due next week, probably Wednesday. All right. You can't do the second half, but I'm going to just introduce to you how you do the second half. All right. We won't get it completely done, but I'm going to introduce to you this last type of bonding called coordinate covalent bonding. All right. That first one, big crash. Okay, so you can put that aside. And now to finish, we're going to talk about something called a coordinate covalent bond. So we've dealt with single, doubles, and triples. And now we're going to talk about, like I said, something called a coordinate covalent bond. It's a little bit different. I would hope you're getting to the end of that first bullet, and as you're reading and writing there, how is a coordinate covalent bond different than the bonds we've talked about up to this point? Why is it different, Cindy? Yeah. Yeah, there's one donating both electrons as opposed to both of them bringing an electron together to share their electrons. So in this case, instead of, like I said, two bringing one each, one of the atoms donates both electrons to the bond. Because we know that a bond contains two electrons, but in this case, like I said, one atom donates both. So here's an example. We're going to talk about the formation of this particular ion here. I've introduced you to this ion. What is the NH4 plus ion? What do we call that? Yeah, Lily? It's ammonium. So that's ammonium. The ammonium ion, all right, and it can bond with nonmetals just like that group 1 ions can bond with nonmetals. This is the way the ammonium ion is formed. First, we have to start with an NH3 molecule, and hopefully you can draw an NH3. We've been drawing Lewis diagrams for a couple of days now, and singly bonded to H, and how do I finish this particular diagram? It's not quite done. Braden? I need a lone pair. Excellent. All right? Now this is what we call ammonia gas. All right? This is ammonia. All right? Now ammonia is a gas, and it's a very pungent gas. If you live on a farm, especially one that has crops, and you grow corn, in the spring after the corn gets so high, the farmers will do a procedure called side dressing the corn, and what they do is they've got this implement that has these knives that dig into the ground, and they inject into the ground ammonia gas, and that is used as fertilizer by the plants, right? It's the nitrogen in it that is used as the fertilizer, and that ammonia really smells and really burns. If you were to, be enveloped with some ammonia gas, you'd likely choke. There'd be no more oxygen around. It would burn your eyes. It would be very, very uncomfortable. You may have smelt ammonia gas if you have ever used ammonia cleaner, right? You can buy ammonium hydroxide cleaner, and when you take the lid off of it, if you've ever smelt it, there's this really strong smell, all right? Many glass cleaners use ammonia in it. So if you have Windex, and if you were to smell that Windex, it has ammonia in it. You might smell it there, all right? My favorite glass cleaner is called Bon Ami. Anybody use the Bon Ami? No, you spray it on the glass, and it has an ammonia smell to it as well. Nobody uses Bon Ami to clean their windows. Justin, when you're cleaning the windows, and I do. Yeah, don't you? No. All right. Well, someday you'll get married, and you'll clean windows, boy, I tell you. Anyway. Ooh, I'm recording this. My wife thinks it's stupid. She never listens to this stuff. All right. I hope. Okay, now we're going to bond with that. We're going to bond with that an H+. All right? Now let's think carefully about what an H+ is. What is a hydrogen plus ion? What exactly is that thing? We're starting with a hydrogen atom. Now we have an H+. What happened to that hydrogen atom in order to make it an H+? What happened to it? Lily, what do you got? So therefore, it's just a nucleus, right? Now that nucleus, and H+ can be made very easily. Acids produce lots of H+. So that H+ is just a nucleus, but it still wants a full outer shell. So how many electrons does it now need to get a full outer shell? It needs 2. And the ammonia has a pair of electrons. And so what happens is, under the right conditions, that hydrogen simply latches on to that pair of electrons. All right? And now that has a full outer shell. Now what we end up with in the end, all right, is we've got a nitrogen. Now it has 4 hydrogens. because it carried a positive charge with it, this whole thing is now positively charged, plus. All right? And this thing contains a coordinate covalent bond. This picture should look a little funny to you. What looks a little strange in that picture, Cindy? Nitrogen normally has 3 bonds in a lone pair. But because a coordinate covalent bond has been formed, the lone pair is now forming a bond. That's how you can tell if a structure has a coordinate covalent bond in it. If there's an atom in there that doesn't look the way it should, according to what we've learned, then there is a coordinate covalent bond in that structure. Okay? So I want to put a little add-on. You can put it down below, but I'll put it right here. N, right, normally has 3 bonds and 1 lone pair. Here, it has 4 bonds. Now, is the nitrogen still happy? How many electrons are around it? 8. 8. 2, 4, 6, 8. So it's still happy, but it's just not in the normal form. If it normally has 3 and 1 lone pair, and here it has 4, we can then say, therefore, it has a coordinate covalent bond. And that's the way you're going to tell. If an atom doesn't look the way it should, then it has a coordinate covalent bond. Now, in the past, we've handed out practice problems, and you'll see it on your sheet, and I'm going to tell you to ignore it. But in the past, we've said, identify which one is the coordinate covalent bond. And you might say, oh, well, that's easy. Right there is the coordinate covalent bond. There's the one that wasn't there moments ago. Again, I'm going to make reference to my model here. If I take this hydrogen off, we can imagine that this is the ammonia. There it is with the 3, and the lone pair actually sticks out the top. Now, if the hydrogen then comes along and forms a coordinate covalent bond, again, now we know nitrogen normally has 3. This guy has 4. That has a coordinate covalent bond. And you might say, that's it right there. There's the guilty one. There's the mooch right there hanging off the side of that pair. But if I then do this, whoops, oh my goodness. And then now I ask, which one is the coordinate covalent bond? There's no way to tell. Because once the bond is formed, you have 4 identical bonds. So the only thing we can really say is, yeah, it's got a coordinate covalent bond in it, but there's no way for us to identify which one it is. All right? Okay, let's do another couple of examples of coordinate covalent bonds, and then we will we'll end there. So coordinate covalent bonds can be formed between atoms or ions that have a lone pair of electrons and another atom or ion that needs a pair of electrons. So let's do another example here. We're going to start with a PF3, and we're going to take a look at what happens if there's an O nearby. So PF3, again, that's a good old regular structure. We look at phosphorus. We see it's in group 15. It should have 3 bonds and a lone pair. So we should be able to draw that up. P, F, F, F. Lone pairs on the F's and a lone pair on the P. Now, oxygen. Oxygen is an atom that has 6 electrons. 1, 2, 3, 4. And because I can't erase, I'm not going to draw on the 5 and 6 yet, but I will put it on the board. Oxygen can do a little trick. Yes, it's got 2 lone pairs, but under the right conditions, it can shift that one over with that one to form a pair, and now you'll notice there's a void with 2 missing electrons. It has a need for 2 electrons. So it can shift that electron over, and now it can form a connection, and you'll notice there's all kinds of electrons to pick by, and it turns out that the phosphorus one is the easiest one. There is an explanation on why it attaches to the phosphorus. We will be able to understand it a little later. I'm going to mention it, but you don't have to worry about it right now. But it has everything to do with this electronegativity. Remember, the electronegativity was a measure of how bratty the atom was and how tightly it held on to its electrons. Fluorine, remember, and if you check your periodic table, has the highest electronegativity. It means fluorine is really holding its lone pairs tight, and they're really close to the atom. So they're not really hanging out to be available for this bonding. Phosphorus doesn't have nearly as high of an electronegativity, so its electrons aren't as close as the fluorines. So as the oxygen goes to make a connection, these electrons are more available than the fluorine's electrons. And that's because it has the high electronegativity. It'll always latch on to the pair that has the lowest electronegativity. So once that connection has been made, we can redraw the molecule, P, F, F, F. Now we've got an O. We have 3 lone pairs due to the F's. And notice O also has 3 lone pairs. All right? Now, oxygen is a neutral atom. It's not like an H+. So the charge of the PF3 doesn't change. We can add oxygens without changing the charge. So there's no charge on this thing. I don't need to put square brackets or anything like that. So if I were to give you that molecule, could you say to me, is there a coordinate covalent bond? Could you answer that? Is there a coordinate covalent bond in this thing? What would your answer be? Yes. What would your argument be? How would you describe how you know that there's a coordinate covalent bond in there? Yep, Marika says phosphorus normally has 3 bonds, but in this case it has 4. Excellent. What else doesn't quite look right? Yep, Christine?
Oxygen has 3 pairs.
Yeah, and it normally only has 2 pairs and 2 bonds. So something's happened to that oxygen as well. In this case, you might be able to identify it because they're not identical. You might be able to say, oh, oxygen, you're the one. There's the bond right there. There's the freeloader bond, I like to call it. With this all being hydrogen, you can't identify. In this case, you might be able to identify. Okay, one more example, which is actually 3 examples. Remember when we were adding and removing oxygens to the polyatomic ions to create the ites and the hypoites and the per-ates? Now we can explain why oxygen can just be added to an ion and not change the charge. We now have the ability to explain that. And the explanation has everything to do with with coordinate covalent bonds. So, example 1, I'm going to start with the chloride ion. I'm going to put down the pen, pick it back up. Cl minus. How many electrons is going to be around a chloride ion? How many electrons is going to be around a chloride ion, Justine? 8, because we've added the 1, right? 1, 2, 3, 4, 5, 6, 7, 8. Square brackets. negative charge. That's just like when we were doing our formation of ions worksheet. And if I have an oxygen nearby that has done the little shuffle, well, you can see there, that's just going to stick onto one of those lone pairs, create a coordinate covalent bond, and that's going to get us to ClO, which is the hypochlorite ion. So we're now working our way up the table. So we'll have this attached here for no reason. And in the next line, I'm going to redraw my new ion here. So take a chloride ion, add an oxygen atom with a coordinate covalent bond, and you get the hypochlorite ion. Cl, now with an O, still 3 lone pairs on the Cl, and 3 lone pairs on the O. The oxygen is neutral. The chloride was negative. What's the charge going to be here? Negative, because the oxygen was neutral and it did not have a charge when it came along and stuck to it. The next slide, I've got 3 and 4 and 5 so that we can do all the rest of them. I'm going to, again, take another O. Again, you might think, oh, this oxygen might just stick right onto the end of that O. But oxygen is very close to fluorine. It has a high electronegativity too. Oxygen holds its lone pairs really tight. Chlorine's electronegativity it is close to fluorine, but it's not as high as oxygen's. So again, the oxygen connects to the chlorine. What do we call it when it's ClO2? It's chlorite, right? So my next slide, number 3, is chlorite. And I will redraw it now with the 2 O's on it. Cl, I got an O there, I got an O there. Still the lone pairs, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And still -1. And as you can imagine, I'm just going to keep adding O's until it's right full. One, 2, 3, 4, 5, 6. Connect it over to there. Redraw for the chlorate. If you were to try to make any of these ions from just chloride and oxygen, the one you get is dependent on how much oxygen you supply to the situation. If you supply lots of oxygen to the situation, it's going to stick to the chlorine and fill it right full. If you limit the amount of oxygen, in the situation, you'll end up with chlorite and hypochlorite. Oh. And it's a little repetitive, but it's not a bad analysis. That guy's going to go all the way over the back there. And the perchlorate. Again, the charge is still -1. I don't know if you guys noticed that, but the charge on all of these ions, chlorate, perchlorate, chlorite, is -1, just like the charge on a chloride is -1. And now we know why, because as we add the O's, it doesn't change the charge. And what's the charge on a sulfate? -2. What's the charge on a sulfide? -2. Because what happens to the charge when we add all these oxygens? Stays exactly the same. All right? I do have one little homework problem that goes with this. That's what I want you to do for homework. Starting with sulfide, draw the Lewis diagrams by adding successive oxygens. All right? And then when you do that, name those ions that you get. Now, some of them you're not going to be able to name because we don't have a name for just SO. All right? Actually, we do. I don't even know what it is. I wonder what it is. I'll have to look it up. So you won't have a name for just SO, but you can name the rest. So, in other words, I'm asking you to do the same type thing we just did with the chlorine, except with the sulfide. Again, I want you to notice that we're starting with a -2 charge as we move our way through. And as you continue to add them, name them. Yep. Nitrogen is a special case. Yeah. But phosphorus, what's it? And what's phosphate? -3. And that has to do, again, with these sublevels. Nitrogen is actually a very small atom compared to these big ones down here, and so its electrons do something different. That's the easiest way to explain it right now without having to talk about the sublevels. And that's why I put nitrate, right, on its own at the top, because it doesn't follow that trend that we've just discovered. Every other one does, though, right? Except carbonate. But notice, carbonate is also a small atom, so it doesn't have the same trend. Yeah. Okay? And you've got, it looks like about 6 or 7 minutes. I don't know when the bell goes anymore, but something like that. You could probably get a lot of these pictures done right now, like with your sulfate ones. Okay? And that is that. You could even work on the top. Oh, I haven't handed it out. I will hand out the sheet, and you can even probably work on the top of this, too, if you want to get it out of the way.